Okay, this is note 7.3 continued for me at least. It may not be, it may not be continued for you. You may not need to write this in your notebook, depending on where you left off last time. The second IMF we're going to discuss is dipole-dipole. And we should say, let's define a dipole first. What is a dipole? You can highlight this if you'd like. I'm just going to do it like that. Dipole simply means a partial charge. Partial charge. Okay. It's found in all polar molecules. Okay. This interaction, we'll just do this. We'll say it happens between all polar molecules. Okay, I went ahead and took the liberty to draw these two polar molecules here. And let's think about what it means to be a polar molecule. All it means is you've got one atom that's hogging electrons. Well, if it's hogging an electron, then that must mean, by its very definition of polar, that it's going to have a slight charge. And the one that's hogging the electron is going to have a slight negative charge. It has to, otherwise it wouldn't be polar, right? So this one's hogging the electron, it's got a slight negative charge. Well, if that one's got a slight negative charge, all the rest of these atoms in this molecule have lost their grip on the electron, so they must have a slight positive charge. And the same must be true in this case as well, right? And so what happens between positive and negative when they interact? Well, there's some attraction there, right? So there's an attractive force between these two separate molecules. That is an IMF, intermolecular force. The bonds holding this molecule together are intramolecular forces, and these are covalent bonds, specifically polar covalent right there, right? So we're talking again, let's be clear, we're talking about this dashed line here. That's this attraction like magnets, like two magnets that these molecules have to one another. And when they're polar, when you've got a polar molecule, there's going to be this dipole-dipole interaction. Okay? It works the same, and if this looks familiar to you, it should, because it works the same way as hydrogen bonding, it's just weaker. Okay, it works the same way as hydrogen bonding, but it's weaker. So if it works the same way as hydrogen bonding, then why do we even need to make a distinction between hydrogen bonding and dipole-dipole? Well, remember, not all polar molecules contain hydrogen. Okay? If it's polar and it doesn't contain hydrogen, then there's going to be a dipole-dipole interaction between those molecules. I'll go ahead and pause and write that. Okay, very important point. Remember, not all polar molecules contain hydrogen. Okay? If they don't, then they will still be attracted to each other through dipole-dipole interactions. Okay, not all polar molecules contain hydrogen. If they don't, they'll still be attracted to each other through dipole-dipole interactions. Hydrogen bonding is just a special case of dipole-dipole. It's a strong version of dipole-dipole. Okay, but not all polar molecules contain hydrogen. Okay, the last IMF is called London dispersion forces. And this happens between nonpolar molecules. Happens between all molecules, but you're only going to really notice it between nonpolar molecules. And the reason why is because it's the weakest of the three forces. Okay, so if it's going on in water, well, you're not really going to notice it in water because water is so polar. You're going to notice the hydrogen bonding, the effects of the hydrogen bonding, the high boiling point, the surface tension, etc., things like that. So let me get back to this then. Why does it happen between nonpolar molecules? Why? If they're nonpolar, they don't have a charge, right? They don't have that partial charge, that dipole, then why would it happen? Why would we see an attraction between nonpolar molecules? And here's the answer. I'm going to pause it and then I'll write to save some time. Okay, the reason why is because the electron is never 100% evenly distributed among atoms and nonpolar molecules, even in a nonpolar molecule like CH4. Let's draw CH4. There's C. I don't have another color for the hydrogens. I'll just draw them smaller like this. Here's CH4, okay? Even in CH4, which is definitely nonpolar, there's still going to be a very, very slight charge amongst the carbon here. Okay, carbon is a little tiny bit stronger than hydrogen. Okay, it's not enough to call it a polar molecule, but there's still going to be some uneven distribution of charge. So because of that, even in CH4, if you get two CH4 molecules close to each other, there's still going to be a very, very, very slight attraction. Not enough for us to draw the dashed lines to show that attraction, but even in these big, specifically like hydrocarbons, the biological molecules, right? You're going to get these types of things. Maybe not the biological molecules, but that's maybe an overreach. But definitely in like hydrocarbons and long polymer type molecules, you're going to get these types of interactions, these London dispersion forces, even though they're not polar molecules. Okay, so go ahead and copy that if you haven't done so already. I'm just going to write here, between these, still a slight attraction, even though they are non-polar CH4 molecules. Okay, you can write that too. There's still a slight attraction even though they are non-polar CH4 molecules. Okay, that's what's going on. A tiny, tiny, tiny attraction there. So now let's go ahead and rank these in order. I've already had this written down, so I'm just going to, hopefully you can see that. IMFs ranked from greatest, well, it should be strongest to weakest. Strongest to weakest. Okay. The strongest of the three is hydrogen bonding. Examples are H2O, NH3, and HF. Specifically H2O. Hydrogen bonding is responsible for the attractiveness that water has to each other, to the other water molecules, right? That's why you form water drops. It's got that surface tension. That's because of hydrogen bonding. That's stronger than dipole-dipole. Dipole-dipole is similar to hydrogen bonding. It's just that it happens between all polar molecules. Hydrogen bonding is stronger. Dipole-dipole is still strong, but it's not as strong as hydrogen bonding, but it works the same way. It happens between all polar molecules. And the last of the weakest of the three IMFs is London dispersion. It happens in all molecules, but especially in nonpolar molecules is where you notice it. Okay, those are the three IMFs ranked in order of strength from strongest to weakest.